Well, hi, I'm Jordan Ando. I'm a first-year graduate student at the University of Hawaii working with Shwai. Um, so possible signatures of lunar polar water ice have been detected in a variety of different data sets. Especially my focus is going to be on the iris spectroscopy data set from M-cubed. However, on Mercury and Ceres, polar water ice deposits have been correlated with an enhanced albedo at visible wavelengths as opposed to IR. And this has not been observed on the moon in long exposure images from the NAC like we saw in a couple presentations ago. So here we have an image of one of those NAC long exposure images with the M-cube detections overlaid on top. So previously, we reattempted detection of water ice in these NAC images, trying to contextualize them with M-cubed. And we did this by looking for the median brightness value at places where ice was presented in M-cubed, and then comparing to the surroundings to see if there was any brightness shift. We found was that in this data set, there was still no significant brightness shift over any just variations in brightness across these NAC images for a large variety of PSRs. This is a very basic method, but we also applied some HAPKE modeling in order to see if it could work. And what we found was that ice mixtures around maybe 15 weight% would be the point where you might be able to detect it using this method. So it's potentially just not a good enough way to go about this. So I'm today going to focus on looking at how modeling and laboratory experiments can help us better understand these PSRs and maybe use these types of data sets to try to look for water ice. And I'm going to be focusing a lot on phase functions of lunar regolith and ice. So we learned a little bit about phase angle a few presentations ago. The phase function describes in HAPKE's model how the light is scattered across the entire range of possible phase angle. And so water ice as a material is known to be very forward scattering, while most measurements of lunar regolith, such as this one from the LROC WAC camera, have been found to be very backscattering. We believe that this difference could potentially help with ice detection because you would be able to compare different phase angles and look to see if it was more forward scattering than you expect. However, we don't know what PSR regolith is like very well. We hypothesize that it might be relatively immature because PSRs are relatively shielded from space weathering. But we don't know exactly how the maturity affects the phase function of regolith samples. So to test this, we got a bunch of Apollo samples in the lab and are able to measure their phase functions to see what the correlation is between maturity and phase function, if there is any. So in order to do this, we focus on exclusively Apollo Highland samples of varying maturity from Apollo 14 and 16. They have a maturity index ranging from 85 at the most mature down to about 20 at the least mature and are depicted here. We measured the phase functions by taking spectra on an ASD field spec 4 from phase angles between 15 and 105 degrees in increments of 15 degrees. We kept the incidence angle fixed and varied the emittance angle in order to account for the non-Lambertian properties of the spectral, and we have these to calibrate. And then in order to determine the phase function, we fit a Henny-Greenstein phase function in HAPKE's radiative transfer model using MCMC, as well as some other parameters that are required in order to produce the fit. So here's an example of the stage that we used to make these measurements, and we control the angles quite precisely by using 3D printed parts. So here are some of the results for fine-grained samples from each of those. For the mature and the immature sample, we had them sieved at less than 150 microns, while for the submature sample, it was less than 25 microns, just due to the availability of the samples. We found that all of the fine-grained samples were backscattering, which is shown by the phase functions here, where the lobe in the backwards direction is slightly larger to getting quite a bit larger. We also see a slight trend in the magnitude of backscattering, as shown by the HAPKE C parameter here, increasing as we go from mature to immature, although this isn't a great direct comparison because this submature sample is of a different grain size distribution. Still, the fact that all of these phase functions that we measured range from being kind of close to neutral scattering here to moderately backscattering is pretty beneficial in making it so that it might be possible to use some of this information if we want to look for water ice. We also examined all of the same samples looking at the coarse grained in order to kind of verify the results with the fine grain. And we see a similar pattern. So overall, the amplitude of the phase function is higher for these coarser samples. And the forward scattering also increases as maturity decreases. So the more mature samples have a smaller C value. So we believe this is good verification that the results from the fine grain samples and the coarse grain samples are consistent. Something to keep in mind is this is all done at 700 nanometers, which is around the main wavelength for both HAPKE and Shadowcam. In addition to this, we did a little bit more HAPKE modeling of ICE-REGOLITH mixtures at the same wavelength in order to demonstrate how this fact might be useful. So we model mixtures ranging from 0 to 15 weight% on this plot. And as we can see, as the phase angle increases, the radiance factor that one would expect at standard viewing geometry changes quite dramatically, even between some very small ICE weight%, unlike with the previous modeling that I showed. One important thing to note is that the LROC-WAC phase function is also very backscattering, as well as the ones we measured in lab. However, the amplitudes of our laboratory phase functions are a lot shallower, potentially due to the fact that we're measuring in the lab and not remote sensing. Still, we believe that comparisons between orbital images of the same location taken at different phase angles may be able to be compared in order to kind of give a new dimension into how we might look for water ice in these sorts of images. Of course, as we saw in the previous presentation, the illumination conditions are very complicated within PSRs. And so all of the phase angle stuff that I've talked about so far kind of is assuming that you have directly illuminated surfaces, which is not the case. So one of the future projects that we're currently working on is to create an experimental setup in our lab that will allow us to test these conditions and help us better understand if what we're seeing with the Apollo samples as we measure them directly illuminated is still consistent with when we indirectly illuminate them. To do this, we're going to be covering essentially a dome around our sample that is going to be 3D printed out of carbon fiber in order to reduce reflection, as well as painted with a very dark black paint. And we'll be able to come up with different scenarios to put inside that dome to kind of simulate the secondary illumination conditions with actual materials in the lab. And so to conclude, differences in ICE and lunar regolith phase functions may assist with ice detection and visible band imagery. By measuring Apollo samples, we still believe that the PSR regolith is probably going to be back to neutral scattering, which is helpful because ice is always going to be forward scattering, but we still need to do more illumination experiments in the lab to better understand these conditions in order to see if all this can actually apply to being used in ice detection images. Great. Thank you very much for listening.